Our next speaker, Professor Ronald R. Yager. Dr. Yager is a professor of information systems at Iona College. He received his undergraduate degree from City College of New York and his PhD from the Polytechnic University of New York. Dr. Yager has worked in the area of machine intelligence for over 25 years. He has published over 500 papers and 15 books in the areas related to fuzzy sets, decision-making under uncertainty, and the fusion of information. He is among the world's top 1% most highly cited researchers with over 7,000 citations. He was the recipient of the IEEE Computational Intelligence Society Pioneer Award in Fuzzy Systems. Dr. Yager is a fellow of the IEEE, the New York Academy of Sciences, and Fuzzy System Association. He has been given a Lifetime Achievement Award by the Polish Academy of Science for his contributions. He served as National Science Foundation Program Director in the Information Science Program. He was a NASA Stanford Visiting Fellow and a Research Associate at the University of California, Berkeley. He has been a lecturer at the NATO Advanced Study Institutes. He has been a distinguished honorary professor at the Aalborg University in Esbjerg, Denmark. He is an affiliated distinguished researcher at the European Center for Soft Computing. Currently, he is Director of Machine Intelligence Institute and Professor of Information Systems at Iona College.
Thank you. I recognize myself. I want to get to my slides. First of all, I'd like to thank you very much for the kind introduction, and of course I'd like to thank Latvi Zadi for his very nice work that has made this possible and serves a basis for most of the stuff I've done. Okay, what I'm going to talk about is the idea of computing with words and granules, and to some extent I think it's sort of a step up from what George gave some very nice ideas, and my work will sort of take advantage of his introduction. What's clear is the fact that human-sourced information, the type of information that human beings provided, human-sourced information, is soft information. It's soft information in the sense that, first of all, it's based on perceptions. Human information is based on human perception. It's also human-focused in the sense that the concepts, the way the information is presented, is in terms of human understanding. It's linguistically expressed. It's in terms of linguistic terms, and it's imprecise and it's uncertain. So soft information is generally granular in nature. It's globs, and perhaps we could see this in the next slide when we talk about granular probabilities. This is usually people don't talk about probability of 0.2. People say about 2. People say close to a half. People say large. These are the type of granules, that the information is not a point but a lump of things. We talk about linguistic terms such as short, medium, tall. These are kind of, again, granulars, concepts that are granulars. Now, granule computing, which is a term actually which is coined by Latvi, is a collection of set-based technologies that allow for the formal representation and manipulation of human-focused linguistic concepts. And it's comprised of a number of technologies, basically fuzzy set, Dempster-Schaeffer theory, rough sets, probabilistic reasoning, possibility, probability, granules. All of these generally deal with granules, and they all put some idea of different types of uncertainties. Okay, Dempster-Schaeffer definitely deals with kind of probability and granulization. Fuzzy sets deal with gradualization and granulization. And this sort of puts all three of them together. Now, I'm going to mainly focus on the fuzzy set aspect of it. And what I want to talk about, main focus of my talk here, is the following. The idea of situation assessment, and this is a very, very important idea, the idea of that given a situation, you want to combine all your information to get an idea of where you are. So situation assessment, which is required for decision-making and other tasks, often involves the fusion of information from multiple sources. So the fusion of information from multiple sources is a very, very important task. And when we have linguistic information, that is information expressed in linguistic terms, as George pointed out, more and more we're coming to realize that this is important information, and we want to include this information in our decision process in a central way, rather than sort of just using it on the outside. We can look at the following here. We can look at this sort of task is the following then. What happens is basically we have information, and we have it expressed in words, okay, and we have a process of translation. We have a process of translation, which for our purposes, I'm going to talk about fuzzy sets, but we could use otherly granular technologies to do it also. And then we take this information here, and we fuse it, we combine it in some way, we do some manipulation which combines this in different ways, and then we sort of get out of here a fuzzy set, and then we take the process of retranslation, which is the process of sort of taking this information and bringing it back to the human. So the human provides it in, and we want to provide it back to the human. This is the general paradigm of kind of using fuzzy sets in reasoning systems, okay? Now, given enough time, I want to talk about first about this end of it, and then I'll come back and talk about some aspects of this. Of course, given the time, there's not that much you could talk about. So let me move forward here. So what I want to talk about, first of all, is on the linguistic presentation of information for human comprehension. So I want to talk about the back end of the thing. And in other words, the following then. Basically, these kinds of information fusion systems, basically, they're manipulating mathematical objects. That is, we've taken fuzzy sets or belief structures, we're manipulating them in some way. And basically then, the result of this fusion is some sort of formal mathematical structure. We combine fuzzy sets or belief structures, we get some sort of formal mathematical structure. And now, the human client, the person who wants this information here, basically of a fusion system, basically wants the answer expressed in natural language or in some way comprehensible to their decision mechanism. In other words, they want the information expressed in a way that they could use it in the task that they're really interested in. Okay, so we want to be able to do that. And so the idea here is one aspect to do this is the problem of what we call retranslation. So retranslation then is a process, again, of converting the formal mathematical representations resulting from information fusion into natural language statements capable of being understood by the human client. Again, now I'm going to talk about, again, fuzzy sets. We have results that are sort of fuzzy sets. We want to be able to retranslate it. Okay, so my point of departure here, and this is just to kind of, I'll go over this rather rapidly, so just the point of departure here is the following then. We have some sort of fusion process. And as a result of this fusion process, we got some value of a variable equal to a fuzzy set. This is a fuzzy set. Now, we have some natural language vocabulary. This natural language vocabulary is the vocabulary of the client. That is the person who we're presenting the information to eventually. He has a vocabulary in which he understands the world. His vocabulary for the world. And we want to eventually present our results in terms of that vocabulary, okay. And in addition, we have basically a fuzzy set representation, okay. We have the fuzzy set representation of the terms in this natural language vocabulary. So the words in this vocabulary are represented in a fuzzy set. So our task basically is to take this value here and represent it by represent it in some element in L. That's what we want to do, so that person understands it, okay. Now, basically, the process is the following. We substitute a proposition V as F, okay, where F is some fuzzy set representation from the vocabulary of the person for A. We want to take this A, represent it in this term, and then we want to express the output as a word from our vocabulary. That's a word that corresponds to this, okay. Now, the key issue here is the substitution. This is the key issue. Given some fuzzy set, we want to be able to find an appropriate representation of a fuzzy set in the language of the client, the person who can understand it. Now, again, this process here, okay, so we want to find then, we're going to say the following then. We want to decide upon the best translation, okay. Now, in general, we have some criteria. You know, the world is a place where we have choices. So generally we have a criteria that we're going to use, or some collection of criteria, in order to make this retranslation. And what I want to do is just briefly go over some types of criteria. Okay. Now, the criteria can be selected or can be default criteria in a system. Now, the types of criteria, at least some of them, they're more involved here, but faithfulness of F to A. That is, what we want to do is make sure that F is true given our data. We don't want to lie. We have to say, maybe we want to express some features of F, and we want to have, some cases, we may have some external goal in choosing the word in addition. So again, let me see what I want. So probably the most important thing is the truthfulness of a retranslation. We don't want a result that is definitely not true. We don't want a result that's not true. So this is generally the most important one. For example, if the result of our fusion process is that John's age is somewhere between 1 to 19, is in a set 1 to 19, we don't want to retranslate this into John is old. I don't want to say John is old. That's clearly wrong. Okay? What I can say is John is less than 20. That's correct. I can say John is over 50. That's correct. But I'm not justified. It's not false, but I can't say that John is 13. Okay? Now what's interesting here, I'm not going to talk about it, but we get, when fuzzy sets, this is sort of a fundamental idea, we get three situations of truth. We get the following. We get the idea that something is true. Okay, this is true. We get something that's false, and we get something that really is undeterminable. We get something that is undeterminable. And this is different in fuzzy logic, and this is another part of the paradigm shift. You have this kind of, I just don't know the answer. A statement is neither true nor false. Okay. Okay, so the key issue here, the key issue in determining the truth of something is what Professor Zadi introduced called the entailment principle. The entailment principle is a fundamental principle, and it says the following. If I know an element is in this set, I could say it's in this whole set, the whole thing. Given that the value of the variable lies in here, I could say that it lies in here. That is, from the proposition V is A, we can truthfully infer that V is in some set bigger than it. This is the idea of entailment. Okay. Now, I think I'll sort of move a little bit on this, not to spend too much time here. Basically, Lotfi introduced the concept of entailment and containment in fuzzy sets, and it's sort of a crisp definition. But this basically is sort of the idea. We have to satisfy this. That's how it. And there have been more definitions of containment. A soft definition of containment, saying the degree to which A is a subset of F. We could introduce this. Using this softer definition, okay, we could end up with saying that this associates with each set F a degree to which it's valid to infer V is F from A. So given some idea of inclusion, I could get idea of degree that this is true, that this statement is true. Okay, and I think I will skip on this thing here. Another criteria that one may be interested in is the idea of closeness. That is, given a statement, I would like to be able to say something that's close to it. That's close to it, okay. Now, though that's not as important as truthfulness. In our society, truthfulness is a very, very important thing. We don't want to say something that's not true. We're able to be vague, okay. So this is a useful criteria. A useful criteria to determine the appropriateness of replacing V is A with F is close to A. Now, this may not be required, but it may be desired. Now, what's interesting is that closeness does not necessarily, truth does not necessarily imply that something is close. For example, given the set F, it's true that it lies in the set B. It's true that it lies in the set B, but B is not close to A, but still true. And sometimes people use things like that as we see, okay? Now, so in order to do that, we need some idea of a measure of closeness of fuzzy sets. So this introduces another fundamental concept of close, how close two fuzzy sets are. And basically, the fundamental unit in discussing the closeness between two fuzzy sets is the difference in membership grades. The difference in membership grades. So you take, this is one fuzzy set, this is the other fuzzy set, this is the membership grade. The difference between the two, is the concept of closeness. And we can measure closeness as something like this. We take the average distance between the membership grades, and we measure that as close. And we can have various different choices here. And this is, I think, a fundamental idea in fuzzy sets, which the fundamental idea in fuzzy sets, I think George alluded to, is that we have freedom. We have freedom in implementing definitions. It's because of the softness of it, you have freedom in introducing definitions. And that means sometimes you choose definitions for various purposes. And the key idea here is, in choosing a definition, and I'll say more about it later, is the idea of co-intention. That is, a definition should capture the main ideas, okay? Should capture the main ideas, for example, but sometimes you use one definition or the other. For example, the idea of, an example of this, a perfect example of that is sort of entropy. Entropy measures the uncertainty of something. But the sum of the squares of the probability also measures the same idea, the variability. And those two definitions are sort of co-intensive. And sometimes you have a choice. So this choice of alpha gives you this idea. And this is something we, okay. Now, now a second concept, so that's two classes of measures of criteria. In selecting the retranslation, we may want to consider some features associated solely with this function. And one idea here is basically fuzziness, okay. The concept of fuzziness, how fuzzy. And this is another fundamental idea in fuzzy sets, which I think really was not available when you talked about the paradigm shift. The concept of fuzziness is not applicable in normal logic. So fuzziness is an important idea here. And fuzziness basically is related to the boundary distinguishing non-membership in F. So saying that John is between 20 and 28 is very crisp. Saying that he's about 25 is more fuzzy. Okay. Now, in general, fuzziness, again, the fuzziness is sort of gradularity, and fuzziness is sort of related to the lack of distinction between a set and its negation. In other words, when you have a set, in classic set, when you take the negation, it's just one is 1, 1 is 0. There's the absolute difference. In fuzzy sets, that's not the case because of that. So the closer the two, the more fuzzy it is. And so let me skip over this and say, so basically the measure of fuzziness then is based on the lack of distinction between F and F its negation. Close to F and F bar, the more fuzzy. So one measure of fuzziness is this, for example. If you take the average difference between a set and its negation, this gives you the measure of fuzziness of F. You notice, by the way, the fuzziness of F bar and F are the same because, okay, so basically then, this type of criteria just depends on F, and it doesn't involve the relationship between F and A. So in other words, sometimes in presenting information, we particularly want to be fuzzy. We particularly want to be fuzzy. Sometimes we don't. Okay. Now, another measure, which is distinct, but sometimes people get it mixed up, is the idea of specificity. Specificity of a fuzzy set related to the amount of information in a statement. It's the amount of information in a statement. So, for example, the statement that Rachel is 32 is more informative than she is in her early 30s. So specificity, this is more specific than this. Specificity measures the degree to which a subset contains only one and one element. So specificity, when you use a word that has one value, that's specific. When you say John is 20, that's specific. When you say John is in 20s, you get more and more unspecific. And again, this is, George has also worked in this area here. Okay, so basically then, fuzziness is related to the type of boundary. Specificity is related to the cardinality of the set. Statement can be crisp and non-specific. For example, John is over 10 years old. It's a very crisp statement, not fuzzy, but it's non-specific. Close to 20 is specific but fuzzy. Okay, again, I'll skip this here. So one way of measuring specificity, one way of measuring how specific, so given a fuzzy set, a word represented as a fuzzy set, given how specific it is, we take the difference between the maximum membership grade and the average of the other membership grades. That gives us the idea of specificity. Okay. Okay. Now, another interesting, now this sort of gets a little interesting here. Another interesting situation, and again, choosing a word to represent some information. You process some information, you have some information represented as fuzzy set. Another criteria one may have is providing retranslations that give desired perceptions. Retranslations that give desired, so you want to take some information and present it in a way to give certain perceptions. For example, advertising and TV always do this. They take cigarette companies, when they were talking about information about, how many people die from smoking cigarettes, they try to present it in a certain way that makes it very, very, give a certain perception. And so perceptions is so if you have, so in some instances then, we have an agenda. So for example, if P is a fuzzy set corresponding to a desired perception, that is, I want people to really think that this is what the fuzzy set, then if I present F, this is the degree to which, given the perception of P using F. Using F, the perception that's P, how close it is, how people would perceive P. Now, what happens then, given these kinds of criteria, given this sort of selecting the best retranslation, then we have an output. We have the fuzzy sets corresponding to the available linguistic terms. We have a collection of criteria. then for each f, we calculate the degree to which it satisfies the criteria. For each f in here, we calculate the degree to which it satisfies the criteria. And then basically we use some sort of aggregation function. We could take the average, or we could take some multi-criteria decision problem. Again, we won't get into that, but we calculate which fuzzy set basically best matches our criteria, and then we select this one. Okay, now I want to just say some words here about, you know, again, in presenting information, sometimes we have an agenda. We have an agenda here of disinformation, okay, disinformation, dissemination. At times we have an agenda when we're expressing this fused information. Again, in other words, we want to convey a particular perception, okay? We want to do it so that we said something that's true, but we haven't really, you know, we give the perception, okay? And so what happens basically then, often we imbue the true value in a larger granule that gives a desired perception without being false. Now, what happens here is the following. Let me just go on here. There's deduction is a process in which, and this is true, given you're in this set, you could deduce. Logical deduction says I can deduce it's in this whole set, okay? Another process, which is reduction. Reduction is a process in that when you're in the orange area, you say you're in the blue area. Now, reduction is really much more prevalent. Human beings use reduction all over the place. Decision making is reduction. When you make a decision, you have some choices and you choose one thing. That's a deduction. People you say something to somebody, sometimes they reduce it, okay? They reduce it. Now, reduction is going from less precise to more precise. From knowing that John is in his between 25 and 35, we infer that he's 30 years old. It's not sound. Reduction is not sound, but it is useful. Most of life involves reduction. When you make decisions, okay? So human beings involve, okay. Now, what I'd like to now do is go to the front end. And now, at the beginning, I spoke about, you know, you did some process and you got out some words, fuzzy set, and you wanted to find a retranslation. Now I want to talk about the beginning. I want to talk about an example of a process in which I start with words, I make fuzzy sets, and I do some sort of aggregation. And I'm going to talk about learning from imprecise, granular, trapezoidal representations. Now, as I said before, huge amounts of information are available. Generally, they're granular and imprecise. Our objective then is to use this information for learning, okay? So what we want to do then, we must represent this information, this linguistic information, in terms of some form of granular object, some fuzzy set. The representation step affords user freedom in selection of the representing granule. So very, very important idea that, you know, there was a very famous book called Escape from Freedom. Those who don't want to escape from freedom better keep away from fuzzy sets. You have choices in fuzzy sets. You have freedom. Okay. Now, it seems now the two major considerations, of course there's maybe more, I'm always reluctant to do things like this, but anyway, there's two major considerations. One is the idea of co-intention. Co-intention is an idea which recently introduced by Professor Zadi, which I think is a very, very important concept, and it says the following. The ability of the representing object to convey the meaning of the information it is being used to represent. So co-intention is that you have some world object, and you represent in some way, you make some model of it. Co-intention is how well that model corresponds to the actual world, okay? And again, you have choices here. The second idea, and the second aspect of it is what I call functionality. Functionality is the ease with which the representing object can be manipulated in the context of the application. So that when you're making a representation, when you're choosing a representation, it has to be somewhat representing what you do, co-intensive, but also you want to keep in mind that you can manage it. So for example, in fuzzy control, people use a lot of exponential functions because it was very easy to manipulate the types of operations you were using. Now, one fairly useful type of fuzzy set, which I'll concentrate on this, is trapezoidal fuzzy sets. Trapezoidal fuzzy sets are fuzzy sets that look like this. They have A, B, C, and D. These are trapezoidal fuzzy sets. Now, what's interesting about trapezoidal fuzzy sets are a number of things. Number one, it's very rich. You can have interval values, You could have triangular type, you could have single points, you could have bookend. Very many types of fuzzy sets are okay. Okay, now what's here interesting is that, what's interesting about fuzzy sets is that we could represent them in level sets. And this was George's talked about level sets. And the idea is basically, the idea is that the level set, as George said, is the sort of the set of elements that have membership greater than alpha. Okay, and so these are sort of level sets. And what's interesting here is the following then. For trapezoids, the level sets are just interval values. The level sets of trapezoids are just interval values. That's it. An upper value and a lower value is an interval value. Now, what that means is that we could do a whole lot of manipulations. For example, what we can do with trapezoidal fuzzy sets, if A and B are trapezoidal fuzzy sets, okay, then what happens is that if you have some arithmetic operations, then, and if you could use, if the end of it becomes a trapezoid, this is called a trapezoidal preserving operation. And this is a trapezoidal preserving operation. And last slide, I think I'll stop here, is basically, it turns out that with trapezoidal fuzzy sets, you could just do like this type of arithmetic operation, for example. You could just do simply on the level sets. So that if you have two level sets like this, and you want to take the combination of these two, if this is the result, all you take is the weighted average of these, and you end up with this fuzzy set. So trapezoidal representation is a very efficient way for processing types of information. And so it's very, very fast. And that makes it very, very useful. I think I get some...
Any questions?